Okay, thank you very much, Bert. I'm very glad to be here. Thanks to all of you for coming. As you just heard, the question I'm going to address is the cerebral cortex the organ of consciousness? Well, the answer for the last 150 years has been yes, of course it is. The basis for that starts, in fact, with our common sense, our experience of consciousness. What you are experiencing right now is made up of perceptual images, predominantly visual images. You're looking at me and your screen now. That's your consciousness. You're also listening to me. That's your consciousness. You also can feel the seat that you're presumably sitting in. That's your consciousness. If you're eating anything, you would also be having tastes and smells. And these are the raw ingredients of consciousness. The five classical sensory modalities constitute the stuff of consciousness. The qualities that constitute our consciousness are the qualities of our sensory perception. When the 19th century anatomists began to trace the connections from our sense organs to our brains, it was clear that they have, not to put too fine a point on it, they have two main destinations. The one is the superior colliculi over here in the brain stem, and the other is the cortex. In the cortex, there is an area dedicated to each one of those five perceptual modalities. And the crucial difference between the cortex and the brain stem, that is to say the superior colliculi of the brain stem, which also have maps of our perceptual modalities, is that if you damage the part of the cortex that's responsible, to which the optic nerve ultimately projects, then the patient is blind. And the same applies to the somatosensory strip. Damage there leads to anesthesia, to loss of sensation in the body. And damage to the auditory cortex leads to loss of auditory consciousness. And deep inside this fissure here, the same applies to an area of the brain, of the cortex, which is responsible for the conscious perception of smell and of taste. The information that goes to the brainstem does not generate conscious images in the way that these cortical regions do. And so it was perfectly reasonable to conclude on the basis of these findings, not only of the anatomical projections themselves, but of the fact that damage to those areas leads to loss of consciousness of those five different qualities. And so it's on that basis that we've believed ever since that the cerebral cortex is the organ of consciousness. Now I'm going to start to problematize this truism. The first problem that I want to draw to your attention is that evidence began to accumulate during the second half of the 20th century and at great pace in the 1980s and 1990s, that you can perceive without awareness of what is perceived, and you can learn from those perceptual experiences without awareness of what is learned. And I'm speaking here specifically of cortical perception and cortical memory. I'll give you an example of just one experiment. If research participants are shown images of faces in a tachistoscope, which is an apparatus which enables the experimenter to flash the visual images extremely briefly, in matters of milliseconds, you can record from the occipital cortex that the visual information has been received, but the research participant says they have seen nothing. That is, if the image is flashed briefly enough. So we know the information has got into the cortex, but it has not generated a conscious image. Now, in the experiment that I'm using as an example, because there really are literally thousands of experiments like this, in a more or less randomly chosen example, the research participants are shown two faces. First, they're shown face A, and underneath that face, it says rapist. And then they're shown face B, and underneath that face, it says philanthropist. Now, remember, we know that they have seen these faces and seen these words, but we also know from their own reports that they consciously have seen nothing. After the tachistoscopic flashing of those faces, the subliminal flashing of those faces and words to the research participants, they are then supraliminally shown photographs of face A and face B and asked which of those two faces do they prefer. They say, I've never seen either of them. I have no opinion on these faces, but they're forced to make a choice. They're told, well, from your gut feel, just tell me, which one do you prefer? And with a very high degree of significance, research participants choose face B. So what that tells us is without any visual consciousness, without any conscious awareness of having seen these faces and read these words, then their behavior has nevertheless been influenced by them. And particularly important to notice here is that we're talking about faces which only the cortex can recognize. It's only visual cortex that can recognize faces. The brainstem structures that I spoke of earlier don't have face recognition capacity. And likewise, only the cortex can read with comprehension. And clearly, these research participants have read with comprehension. And they've associated what they've read with the face that they've seen, and they're subsequently able to recognize that face because they prefer face B because of what they've read about it over face A because of what they've read about that face. So this is the sort of evidence that accumulated in the 80s and the 90s that led us to realize that the cerebral cortex is capable of performing its perceptual and cognitive functions without consciousness. So I told you I'm going to problematize the generally accepted truism that the cortex is the organ of consciousness. And the first problem that I've pointed out is that the cortex can perform its perceptual and cognitive functions without being conscious. So it's not evidently an intrinsically conscious organ. It's an organ that can perform these functions without being conscious, which actually gave rise to the not unreasonable question, well, then what is the consciousness for? What does it add? What does it do? It's such a troublesome thing, consciousness. Why do we need it at all? I'll come back to that question later. Now, the second big problem for the claim that the cerebral cortex is the organ of consciousness came to us long ago in 1949. That was the year in which two American physiologists, Magoon and Maruzzi, did some experiments on cats. They were using the EEG, which measures the level of activity in the cortex through the cranium with the electrodes placed on the outer surface of the head. And they placed this apparatus on these cats, and they were trying to determine what happens if the cat is deprived of incoming sensory information. Their prediction was that the cat will at the least fall asleep, if not fall into a coma. It will lose consciousness in the form of sleep, and the EEG will accordingly, the level of cortical activity will go down. That's not in fact what happened. So it seemed as if the state of consciousness is not dependent upon information flowing in from our senses. So they then did a few other experiments trying to see, well, what is the part of the brain then that's responsible for consciousness, for wakefulness, and they alighted upon these structures colored in purple here in the brain stem, now known collectively as the reticular activating system. They alighted upon these structures because they found that when these structures are damaged, the cats went into coma. So that was a whopping great surprise, because, as I said to you at the outset, we've always known that consciousness flows in with our sensory information. But this part of the brain, the reticular activating system, the innermost core of the ancient brain stem, is not receiving sensory information. But it seems as if this part of the brain is absolutely fundamental to consciousness, because if it's damaged, the cats fall into coma. And what Magoon and Maruzzi also showed was that if you make a small incision above the reticular activating system, disconnecting the cortex from reticular activation, then the cortex loses all consciousness. So it became clear that the consciousness of the cortex is generated endogenously. It comes from within the brain and from a very different part of the brain, from the reticular activating system, which is why it got that name. It activates the cortex. Nowadays, we know more precisely that within parts of the reticular activating system, damage as small as 2 cubic millimeters in extent, the size of a match head in the parabrachial complex back here, is enough to induce coma in human beings. Because what Magoon and Maruzzi observed experimentally in cats, we've observed innumerable times since then in naturally occurring lesions in human beings, that the state of consciousness is entirely contingent upon arousal by the reticular activating system of the cortex. So, as I said, this was a great surprise. So what did Magoon and Maruzzi make of their findings? What they made of it was the following. They said it seems as if we should divide the consciousness into 2 different aspects. The consciousness that we'd always, the phenomena that we'd always used the word consciousness to denote, they're now called the contents of consciousness. They said that the contents, that is to say, the actual raw ingredients, the actual qualitative stuff of consciousness, the phenomenal contents and qualia is generated by the cortex. But the brain stem, the reticular activating system in particular, is responsible for the level of consciousness. It provides a sort of background quantitative power source, but not consciousness itself. They saw this as a sort of prerequisite, a precondition. First, the cortex has to be powered up. Only then can it generate phenomenal consciousness. But the phenomenal consciousness itself doesn't come from the brain stem. The analogy that's frequently used to describe what I've just tried to convey to you is that of a television set that has to be plugged in to a power source at the wall before it can do its televisual thing. Unless you plug it in and switch it on, then of course it can't generate televisual images. It can't transmit them. It can't produce the content of these programs that we watch on television, because a prerequisite for a television to do its televisual thing is that it has to be powered up. So the reticular activating system was seen as this sort of power source for the cortex, which is the real organ of consciousness. It's very important to recognize that nobody, this is not controversial, everybody agrees that the reticular activating system its activation of cortex is an absolutely necessary precondition for the cortex to be able to generate consciousness. However, it does not generate any qualities and any contents of its own. It's just a prerequisite, something that stands outside of the actual contents and qualities phenomenology of consciousness. So that is how we, in the middle of the last century, how we resolved the surprise that it turned out that the reticular activating system is the part of the brain that, when damaged, leads to coma, and that if disconnected from the cortex can't generate consciousness. That's how we resolved the problem. Now, remember what I said to you when I showed my first slide. This slide on the screen now it dates to 1940 or pertains to findings from the 1940s and 50s. But in the 1980s and 90s, we have made the additional observation that, in fact, the cortex can process information at a very high level of complexity, like face recognition and reading and with comprehension and learning and so on, from those kinds of perceptual experiences, that all of that can go on unconsciously. So these are the two problems with the theory that I'm wanting to use as a sort of preface to what I'm going to show you now. If it were true that the cortex is the organ of consciousness in the sense that there is no phenomenal consciousness, your consciousness has no quality and no content unless you have a cortex. If that were true, then what would happen if you were to remove the cortex? The prediction would be, well, then you would have coma, or something that we call the vegetative state. The vegetative state is also described as non-responsive wakefulness. In other words, there would still be a sleep-wake cycle, the autonomic sleep-wake cycle, but there would be no phenomenal consciousness. There would be a sort of blank wakefulness. And this is what we see in patients in a persistent vegetative state, non-responsive wakefulness. That's the very least we would expect if the cerebral cortex was the organ of conscious qualities and contents. Then patients with no cerebral cortex should have no conscious qualities and contents. They should just have, at the very most, this kind of blank wakefulness. But that's not what we see. If you remove the cortex from a neonatal mammal, it continues to be behaviorally responsive. And it continues in particular to show the full range of basic emotions. That is to say, they show fear, they show separation distress, they show pleasure, they show hunger and thirst, and they even play, they even copulate, they even raise their young to maturity. So emotional behaviors, of course, these animals are not normal because they are blind and deaf and whatnot. But all of these emotional behaviors are still present in them. Those are animals. Of course, we can't remove the cortex in human beings, but there's this condition known as hydranencephaly, an instance of which you're seeing on the screen right now, in which children are born with no cerebral cortex, usually because of massive stroke in utero. There are a variety of causes, but usually it's a massive CVA in utero, and the cortex is reabsorbed. So these children have an intact brain stem, but they have no cortex. So let's see what happens with these children. Remember what I told you, the prediction is that there should be nothing it's like to be these children. They should have no, their consciousness should have no content and no quality. Here's the child whose scan you just saw. As you can see, she's awake. In other words, she wakes up in the morning and she goes to sleep at night. In that sense, she has a level of consciousness. She has wakefulness. But much more importantly, please note the second slide, she is responsive. When you place her baby brother on her lap, she goes, ah, she likes it. She shows pleasure. And it's not only this child, and it's not only this instance that I have on the screen now. All of these children are like that. They are emotionally responsive. They are emotionally responsive in situationally appropriate ways. In other words, if you clap your hands, they startle. If you tickle them, they giggle. If you place the baby brothers on their laps, they show this nurturant pleasure. If you take the baby brother away, they arch the back and fuss and complain, and so on. They show a full range of basic emotional responsivity, and they show these emotional responses in situationally appropriate ways. So it cannot be said that they are in a vegetative state. Remember, the definition of the vegetative state is that it is non-responsive. These kids are responsive, but they're responsive emotionally. Now, emotional feelings, of course, have phenomenal quality. They are a mental content. It's just that they're not an exteroceptive perceptual content. They are an endogenously generated affective quality and content. Before I move on, I'm sure that some of you are puzzled. How come these children are responding to these stimuli if they're deaf and blind and whatnot? And that's because of the thing I told you about at the beginning. I said that our sensory organs send their inputs not only to the cortex, but also to the superior colliculi in the brainstem. So in these children who have no cortex, of course, she can't see her brother, but nevertheless, she's receiving unconsciously, she's receiving visual information about what's going on. And she responds emotionally to that information. On this example, I'm showing you the visual pathways. The same applies to the tactile pathways and the auditory pathways and so on. They project to the superior colliculi, so they're receiving information about the outside world. It's just that the information they receive is unconsciously processed. But they are not unconscious. They are conscious beings. They are affectively conscious beings that feels like something to be them. They have emotional feelings and emotional responses. They just don't know what they're responding to. They don't know what their feelings are about. So it's not that they are normal, but it is that they are conscious. They are phenomenally conscious. That it's not true that they only have a blank wakefulness, that they only have this quantitative power supply. Their consciousness has quality and content. Now, I'm very much aware, in fact, my colleagues have made me painfully aware of the fact that we don't know what it is like to be these children. I must tell you that most of my colleagues who say, how do you know these children are conscious? You can't be sure that they're not just showing reflexive and instinctual responses. You can't be sure that there's actually some phenomenal feel to these children's responses. Of course, you can't be sure, but I must tell you that the vast majority of these colleagues who say that have never interacted with these children. It is really a stretch. If you've actually had the experience of interacting with a hydranencephalic child, to believe that they are in fact zombies, which is the term that the philosophers in this area use. They call them philosophical zombies. In other words, from the outside, there's all the behavioral evidence of consciousness, but all is in fact blank within. It's a bit like with our pets, dogs and cats and so on. Of course, you don't know that they're conscious, but from their behavior, everything suggests that they're feeling joy or sadness or pain or whatever. But of course, we can't know. So what do we do about this? This radical skepticism? Well, if we're not philosophers, but rather scientists, what we have to do is design experiments which get around the fact that in these cases, these children have no cortex. They therefore can't tell us what it is like to be them. But there must be other methods we can use to test the competing hypotheses. The hypothesis my hypothesis that in fact the brain stem is generating consciousness, which has a quality and a content, compared to the competing hypothesis that it's just a blank level of consciousness, a quantitative dimension with no quality and content. Before I go into the evidence for and against these competing hypotheses using other methods of testing them, I want to just pause to make sure that I'm getting across a central point. Everybody agrees that the brainstem arousal is prerequisite for cortical consciousness, that cortical vision and hearing and whatnot cannot be conscious. It is not conscious unless it is modulated, aroused, activated by the brainstem. But this was construed as a simple power supply. What I'm saying on the basis of the evidence I've shown you so far is that all you need is a brainstem to be able to be conscious and to have feelings. And if this power supply, in fact, generates quality and content of consciousness called affect, called feeling, then feeling, affect, is the prerequisite for the other forms of consciousness. So as I said, everyone agrees that brainstem arousal is prerequisite for cortical consciousness. But I'm saying that prerequisite arousal does have content and quality, and therefore affective content and quality is the foundational form of consciousness. And that is my main claim. So now let's look at the evidence. Of course, I can only give you a selection. I've selected a few striking instances which exemplify the sort of evidence that we've collected over the last 20 years. So the first is the lesion evidence. I've already told you, damage to 2 cubic millimeters of the reticulate core of the brain stem obliterates consciousness entirely, but removing the whole of the cortical expanse does not obliterate consciousness entirely. So that's the lesion evidence, but I've told you about the skepticism that my colleagues have expressed in response to that. And so now I'm going to show you how we can get around that skepticism. On my hypothesis, if you were to take an electrode and stimulate the reticular activating system, and by the way, the same turns out to apply to the periaqueductal gray. So the reticular activating system is over here, and then the periaqueductal gray is just adjacent to it and adjacent to the superior colliculi. All of these structures, I'm claiming, are responsible for affective consciousness, the basic form of consciousness. The competing hypothesis is that no, they're just a power supply. If you were to electrically stimulate these structures, what would happen? I would predict that you would generate feelings, rather intense feelings, and a wide range of feelings. Whereas the competing hypothesis, the one that the mainstream view, would be, well, it would lead to increased or decreased wakefulness, just a change in the level of consciousness, not in its content and qualities. So what happens? This part of, and again, remember, I'm just giving you one example. I don't have time to give you a full range of examples. So this is indicative of the sorts of evidence that we've accumulated. If you put an electrode into this part of the brainstem, part of the reticular activating system known as the substantia nigra, I'm saying it should generate some sort of intense feeling. And the competing hypothesis is, well, it should do something to the level of arousal of the patient. So obviously you can't go poking electrodes into people's brain stems for purely research interest purposes, but there are conditions, clinical conditions, in which we have to do that. One of them, which is why I mentioned the periaqueductal gray, is for the relief of chronic pain. If you stimulate parts of the periaqueductal gray, you can suppress chronic pain, which is in itself evidence of what I'm talking about. But for the treatment of Parkinson's disease, we frequently put brain stimulators into a structure just above the substantia nigra, called the subthalamic nucleus, which is it's a motor structure. It doesn't have to do with, it's not part of the reticular activating system. And sometimes these electrodes go just a few millimeters further than the surgeon intended. And here's one example of what happened in this particular case, a case of a 65-year-old woman who had Parkinson's disease, but had no psychiatric history at all. This is what happened. Within 5 seconds of the electrode being switched on, the patient's face expressed profound sadness. Although alert, she started to cry and verbally communicated feelings of sadness, guilt, and uselessness, hopelessness. She said things like, "I no longer wish to live, to see anything, hear anything, feel anything. When asked why she was crying and if she felt pain, she said, "No, I'm fed up with life. I've had enough. I don't want to live anymore. I'm disgusted with life. Everything's useless, always feeling worthless. I'm scared in this world." When asked why she was sad, she said, "I'm tired. I'm crying over myself, of course. I'm hopeless. Why am I bothering you?" So this response can only be described as depression. Within 5 seconds of the electrode being switched on, the patient fell into a profound state of depression. In fact, suicidal depression. And she had never experienced anything like this in her life before. The depression disappeared less than 90 seconds after the stimulation was stopped. Now, very generously, this patient allowed the surgeon to then stimulate again in this region and in the subthalamic nucleus without her knowing where the stimulation was being applied. And every time that it was applied to the substantia nigra, to this part of the reticular activating system, she fell back into the same terrible depressive state. And this never happened when the stimulation was applied to the subthalamic nucleus. So my prediction is confirmed. This is what happens. If you stimulate reticular activating nuclei, you generate intense emotional responses, which these patients can report because they have intact cortex. And remember, I said the same happens with the periaqueductal gray. These brainstem structures, when stimulated electrically, you produce the most intense and the widest variety of emotions, of affective feelings anywhere in the brain. So the competing hypothesis that this is responsible for a level of wakefulness as opposed to a phenomenal content and quality is clearly disconfirmed, and my hypothesis is what is upheld. Now we go to another method. What would happen if you image the brain functionally with fMRI or positron emission tomography? These methods enable us to see when a patient is in a particular mental state. You're able to see what part of the brain is activated in conjunction with that mental state. In other words, not to put too fine a point on it, what part of the brain is responsible for producing the mental state that the patient reports and the behaviors that you observe. If we were to put people, research participants who are in intense emotional states into a PET scanner, my prediction would be you would see activation in the brain stem, not in the cortex. And the alternative hypothesis is, well, you'd see it in the cortex because the cortex is the organ of conscious qualities and contents. So here's an example of one such study. Here are 4 intense emotional states: sadness, anger, happiness, and fear. And in all instances, the activation is in the brainstem. It's in the brainstem, in the subcortical regions in the brainstem, and of course the pathways ascending from the brainstem, but not in the cortex. In fact, in many instances, the cortex is deactivated. So again, the hypothesis that the affect is actually generated in the brainstem by the brainstem is consistent with these images, and the idea that it is generated, the consciousness is, the feelings are generated in the cortex is inconsistent, incompatible with these findings. Again, the important thing here is here we have intact cortex. These patients can tell us what they feel. These research participants can tell us what they feel. So we're not guessing. They say, they show, they are in these intense emotional states. And this method enables us to see which part of the brain is responsible for those states. The last part of the last type of evidence that I want to show you has to do with chemical manipulations. If the neurotransmitters that are sourced in the reticular activating system, if you increase or decrease the levels of these neurotransmitters in the brain, then on my hypothesis, this should have consequences for the emotional feelings of the patient. And on the old hypothesis, the cortical hypothesis, the hypothesis that the reticular activating system is responsible only for the level of consciousness, for wakefulness, without content and quality, then the manipulation of these neurotransmitters, pharmacological manipulation of them, should lead to increased or decreased wakefulness. But that's not what happens. And that's why these neurotransmitters, serotonin is perhaps the best known in this regard. Antidepressant drugs increase the availability of serotonin in the brain. Antipsychotic drugs they reduce the availability of dopamine in the brain, or at least in certain parts of the brain. So antidepressant drugs, antipsychotic drugs, and anti-anxiety drugs, in the case of noradrenaline, all of these neurotransmitters their source cells are in the reticular activating system. The manipulation of these neurotransmitters forms the mainstay of psychiatric medication. These are treating emotional disorders. These are doctors for feelings. And so clearly, why would they be giving drugs that act on the neurotransmitter systems that are sourced in the reticular activating system if all it was responsible for was a background level of consciousness, blank wakefulness? That might make them of interest to anesthetists, but it wouldn't make them of interest to psychiatrists. And yet this is what psychiatrists are tinkering with every day for the treatment of emotional states. So on the basis of all of this evidence, I think that we have to conclude that the brainstem, which everyone accepts is prerequisite, brainstem arousal is prerequisite for cortical consciousness. I'm saying that prerequisite form of consciousness has a content and a quality that is affect, feeling, raw feeling is generated there. And this is because it is a precondition for all the cognitive forms of consciousness. We have to say that affect is the foundational form of consciousness, and that the organ of consciousness, therefore, is in fact the brainstem, at least its reticulate core. The cortex is secondarily rendered conscious by being activated by this system. But remember that the cortex is capable of performing its cognitive functions without those cognitive functions necessarily being conscious, as I showed you at the outset. So the cortex is not the organ of consciousness in the sense that it is not intrinsically conscious. It is rendered conscious by brainstem activation. Brainstem activation is the actual source of consciousness. It is the actual foundational form, the actual basis of all consciousness. I would say, I would put it like this. On the basis of brainstem arousal, if I translate it into words, you feel like this. I feel like this. It just is a raw feeling. And then secondarily, as the brainstem activates the cortex, we can say, I feel like this about that. In other words, we feel our way into our perceptions and cognitions, which are otherwise going on unconsciously. I hope that I've made that last point clearly, because that's the essential mechanism as far as I can see. The essential mechanism of consciousness is feeling. It's first affective feeling. I feel like this, and then it is applied to cortical perception and cognition. I feel like this about that. The cortical images, once rendered conscious, provide the context for the feeling. They explain the feeling. Like I said about those hydranencephalic children, they feel like something, they just don't know why. They don't know what the feelings are about. Please note, I'm not saying the cortex plays no part in consciousness. And I, for one, am very grateful to have a cerebral cortex. I don't want to do without it, because it adds all of this additional functionality that I can know what my feelings are about, that I can hold in mind. What am I going to do in the world about this feeling that the world is currently producing in me, or that I'm producing by dint of the way that I'm interacting with the world? That is certainly additional functionality of a very important sort, but it is simply not true to say that the cortex is the organ of consciousness. The organ of consciousness is the reticulate brainstem core, which then applies its feeling to cortical perception and cognition. So that's the basic argument that I wanted to present to you. I know I have only 3 minutes left, so I just want to conclude by pointing out that what I've just said to you has implications for the so-called hard problem of consciousness. David Chalmers, the philosopher, in 1995 formulated what he called the hard problem of consciousness. I don't have time to go into all of the nuances of this philosophical argument, but it basically boils down to that last sentence on the slide. He says there is no cognitive function such that we can say in advance that explanation of that function will automatically explain experience. And this derives from observations like the ones that I showed you in that review article that had the title Perception Without Awareness of What is Perceived and Learning Without Awareness of What is Learned, that the explanation of the mechanisms of these cognitive functions doesn't tell us why it feels like anything to perform them. And this is the hard problem, is how and why do the feelings come, or does the phenomenal experience come about? And here's what Chalmers is saying, that there's no cognitive function that's such that we can say in advance that explanation of that function will automatically explain experience. And I'm saying, well, yes, that's true of the cortex, because the cortex is not an intrinsically conscious organ. It can perform its functions unconsciously, and so we're looking to the wrong place if we're trying to solve the hard problem of consciousness. We should rather look to the affective brainstem, because if you replace Chalmers's term cognitive with this term affective, then I think his argument suddenly loses a great deal of its force. To say there is no affective function such that we can say in advance that explanation of that function will automatically explain experience, I think is a nonsense, because there is such an affective function. It's called feeling. I'm saying in advance that explanation of the function of feeling will automatically explain experience, because you have to feel a feeling. It is an intrinsically conscious process, an intrinsically conscious function, unlike vision and perception and learning in general, which, as I've now said repeatedly, can go on in the dark. Feeling cannot. And this is not a semantic or a linguistic argument. I've showed you the physiological and anatomical evidence for it, that the part of the brain that generates feeling is also the part of the brain that generates consciousness. That is its basic function. The activating system is not called activating for nothing. So thank you very much for your attention. I look forward to some questions.
Thank you very much, Mark. Very interesting talk. Are there any questions? Guy Mitchley.
Thanks very much, Mark. It was absolutely fascinating. So I popped my hand right up immediately because I've got to head off to a thing at 6. But a couple of things. I've got a son who is engaging in, or he has to take various drugs because he's on the spectrum, and how it affects his functioning. I find it extremely interesting that this thing's traced all the way down so deeply in the brain. But I wanted to just quickly talk, see what you thought about the work of a guy called Ian McGilchrist, who has done some work on the divergent functions of left and right hemispheres of the brain, with the left hemisphere being more focused on immediate gratification and objective achievement. The right hemisphere being focused more on big picture thinking. And he argues that that's an evolutionary sort of response. And it's very interesting to me that the left and right, these left and right brain functions would actually interact with the brain stem. And what you think about that? Is it a complete? Is it a bull dust story, or is this is there any value in pursuing this sort of line? Thanks very much.
Thank you. I know Ian McGilchrist, and it's not bull dust. I would just reiterate what I said toward the end of my talk, when I said I'm not saying the cortex plays no part, and I am very grateful to have a cortex. It certainly does something, and it does something of enormous value, but it is not the source of consciousness. It is not the organ of consciousness. It's not where consciousness is actually generated. But the sorts of things that Ian McGilchrist talks about in terms of the different contributions of the left and right hemispheres to cognition is very interesting and very important. It's just got to do with much later stages of our evolutionary history, because let me point out, in case there's anybody in this meeting who's not aware of this, that the reticular activating system and periaqueductal gray are found in all vertebrates. Unlike cortex, which is pretty much a preserve of mammals. So we're talking about a function which has been with us for 525 million years or thereabouts, unlike the sorts of things that the cortex contributes. But that's not to demean what the cortex contributes. And I read Ian's first book, The Master and His Emissary. I ordered the second one, but when I saw it, I mean, it's 2 big fat volumes. I will have to wait for my December holidays to read it. But I'm actually going to be having an online conversation with him, a public conversation with him on it. So I'll have to start at least dipping into it. I have every respect for him. Thanks very much.
Please let us know when that happens. I'd love to tune in. He is an ex. He spent some time here at Stias.
Yes, he came to my farm. Yes, yes.
So
any other questions? I see there's something.
Yeah, there's a question in the chat. Maybe you can answer that, or David, do you want to ask the question, or?
No, I think I can. It'll be easier to read. I hope I have articulated it carefully and it's within scope.
Okay, so I hope this is in scope of the current topic and have articulated my question adequately. Would you speculate on an issue being debated globally, whether lower vertebrates and invertebrates, sorry, I've got a little something covering my screen there. I guess you're saying invertebrates, might be sentient and capable of consciously perceiving pain? And if so, where in the neural system this might occur? And how might one experimentally determine this? So let me say, first of all, which is slightly outside, your question is absolutely on theme. But let me give an answer which doesn't initially it doesn't directly address your question, and then I will come to your question. In human beings, there are broadly speaking, two pain pathways, and I'm really simplifying, and I'm building this on the model of what I said earlier in my talk. There are nociceptive pathways that go to the cortex, to the somatosensory strip in the parietal cortex, and there are pathways which go to deeper brain structures, centrally, including the periaqueductal gray. And if you lesion the pathways going to the periaqueductal gray, the patient is able to say, yeah, there's pain in my left finger, but I don't care about it. It's not unpleasant. I'm just aware that there's pain in my left finger. And conversely, if you lesion, or if there is a lesion to the parietal cortex concerned, the patient will feel pain, but they won't know where that pain is located. So the cortical part provides sort of topological information about the location of the pain, but it isn't, the affect is not generated in the cortex. The affect is generated in the brainstem, so I just wanted to say that first of all. Now, secondly, also a sort of a general point, which I may make a more direct link to your question, is that the philosophers speak of, the problem of other minds. The mind is something subjective. You can only therefore ever observe your own. And so how do we know whether not only any other creature is conscious, how do we even know if we each other are conscious? I can't, David, directly observe what it is like to be you. I can't observe your mental state, so I can't know empirically that you are conscious. I infer it from all sorts of evidence, like, first of all, well, you're a human being, you've got the same anatomy as me, and this, you behave in the same way as me. There's every reason to infer that you are conscious. So this is the knowledge that we've gained about where consciousness is generated, by what machinery, by what anatomical mechanism, is invaluable objective information for determining which creatures have consciousness and which do not, or which are likely to have consciousness and which are not. So the fact that all vertebrates have this same machinery is good reason to believe that all vertebrates are conscious. And then it's not just a matter of abduction. It's also then a basis for formulating falsifiable predictions. So that, for example, I predict that if I lesion this structure in a fish, the fish will fall into a coma, which is always what happens. And if I were to stimulate the ventral periaqueductal gray in a fish, the fish will seek out that stimulus because it's pleasurable. And that's what happens. And if you stimulate the more dorsal parts of the periaqueductal gray, you predict that the stimulus will be aversive and that the fish will avoid it. And that's what happens, and so on. So I think that the evidence that all vertebrates not only feel pain, but that they feel actually a range of emotions, I think the evidence is very good. Very strong. I myself actually, I would go so far as to say 99% certain that all vertebrates have a range of affective conscious states. Now, when it comes to invertebrates, it becomes more difficult because they don't have homologous anatomy. That does not mean they're not conscious. It just means we can't use that nice solid basis for formulating testable predictions, which we can then, like stimulation experiments and so on. But that doesn't leave us entirely in the dark. We can also formulate other ways of determining the presence or absence of feeling. I, for one, think that feeling is the basis for voluntary action. If all you had was automatic responses, you wouldn't need to feel. If every single time you have this kind of stimulus, you produce that kind of response, then there would be no need for feeling. I think that what feeling contributes is it tells the animal, the animal is able to, feel how well or badly it's doing. So if it finds itself in a novel situation, and heaven knows there are many of those in nature, if it finds itself in an unpredicted situation for which it doesn't have a pre-programmed reflex or instinctual response, what does it do? It has to behave randomly, and most of the population in that situation will die. There'll be a small percentage who happen to do the right thing, and they will survive and they'll reproduce, and then over phylogenetic time, but through natural selection, we gradually are able to deal with wider ranges of environmental situations. What feeling enables is the creature, because it doesn't have a pre-prepared response, it behaves stochastically, but then feels which of those behaviors is meeting the need and which of the behaviors is not meeting the need. That is the function of feeling. Feeling pleasurable feelings or unpleasurable feelings are the way in which we become aware of the most basic value system underpinning all biological life, namely that it is good to survive and reproduce and bad not to. So unpleasurable feelings mean I'm moving out of my viable bounds. And pleasurable feelings mean that I'm moving back towards them. And that this enables you to, by dint of feeling your way through a novel situation, you're able to make choices. Choices have to be underwritten by a value system. There has to be a good and a bad in choices. And this makes voluntary behavior possible. So I'm sorry, I'm giving quite a long-winded answer when I say, so basically I think that where you see voluntary behavior, where you see a creature that is able to solve problems in unpredicted, uncertain situations through novel solutions, I think that that's not as secure as in the case of vertebrates, but I think that that's a reasonable criterion for taking an educated guess at it. On the basis of that criterion, I hope I don't lose all of your confidence when I tell you this. Certainly, I do believe that some crustacea are conscious. I think that many insects are conscious, but not conscious like we are. You know, they just have raw feeling, which gives them this important functionality of being able to feel their way through the problems that confront them, which are so much simpler than the ones that confront us. So thanks for that question.
Thanks, Mark. I think we've got time for one more question. Roshni, were you going to ask a question?
Yes, thank you, Mark. Thank you very much for the fascinating talk. Really interesting. I'm just curious why you perhaps left out the limbic system. It is also a bit primitive, is it not? And it's above the brainstem, but yet it is involved with emotion, memory, and arousal. Would you mind commenting as to why that was not part of your take?
Sure. Actually, the only reason is because of limits of time. I just gave the headlines. I just gave the simple headlines. So I was talking about cortex and brainstem. I should really have talked about cortex and cortical neurotransmission versus subcortical neuromodulation. There are neuromodulation, in other words, the arousal, the modulation of this message passing that goes on in the higher brain. It even begins lower than the reticular activating system. For example, in some of our glands, you know, the adrenal glands and the gonads and the thyroid and so on, these are contributing to arousal through hormonal mechanisms. The reticular activating system is really the big ticket item. I mean, that's where these 5 main neuromodulators, dopamine, noradrenaline, serotonin, histamine, and acetylcholine. Those are the really big ticket items. But then at the level of the limbic system, which are also modulatory systems, but they're much more specific than the non-specific arousal systems of the reticulate core of the brainstem. There, the modulators are mainly neuropeptides, of which there are more than 100 in the brain. So, I mean, a very good example is mu opioids. Everybody knows that opiates affect feeling, affect nociception, pain. They also affect sort of panicky anxieties. It can be calmed by opiates. Separation distress is basically the biological type of anxiety there. But you know, so there's as I said, there are over 100 peptides. There's a great range of specific emotional systems in these subcortical limbic structures that you could see as a kind of an extension. I just want to mention in closing one last point, that all of those brain circuits for the basic emotions, those limbic circuits that you're referring to, all of them ultimately send their residual error signals to the periaqueductal gray. The periaqueductal gray is a sort of like a great assembly point for all of these limbic homeostatic mechanisms, which are the mechanisms for not bodily affects, but rather emotional affects for the most part. So again, sorry for my keeping things simple. You're absolutely right that the reticular activating system, although it's the crux of the brain's arousal states, the brain's arousal machinery, it's not by any means the only arousal machinery. There's lower and higher machinery too, but it's subcortical. Thank you.
Thank you very much.
Well,
thank you.
Well, thank you very much, Mark. It was a wonderful talk. Thank you for presenting it. Thank you for answering the questions. And the one thing that rests for me to do is thank all of the people who attended. And we'll be back on 20 September with a talk by Robin Catchpole on new views of our universe with the James Webb Space Telescope. So completely different talk, but definitely also very interesting. Thank you very much for attending.
Thank you.
Have
all
a great
very
evening.
Much. Thank you. Bye-bye.
Bye-bye.